All right, we're going to go ahead and get started and have a conversation with our panelists today, a couple of valued TRS colleagues of mine. So we definitely expect audience participation. So I would ask everyone who is logged in today to be aware of the Q&A chat box down at the very bottom of your Zoom experience. Please open that up, and as you have questions for our panelists today, I would encourage you to go ahead and type them in there. We will either answer them directly during our planned discussion, or we will set aside some time at the end of this webinar to address questions that we receive. And of course, after each one of our webinars, we do like to send everyone a copy of answers to these questions. Additionally, just some extra logistics about Zoom. I do find the view settings in Zoom are a little jarring to see the presenters jumping out at you. I would certainly recommend that you take the time under your view settings to change your view to gallery. That'll allow for both of my colleagues, Susan and Chris, to come into view and be a part of the conversation that I have planned today. So go ahead and get that set up. And we will begin our discussion on thermal remediation in Bedrock. TRS really prides ourselves in heating up bulk material, whether it be sand in the Vado zone, clay, rock, etc. It is quite easy for us using electrical resistance heating and thermal conduction heating to heat that material. It's what we do as a thermal remediation company, the entire rock matrix, not just the fractures or where the water moves through the rock. It is truly the entire bulk matrix of material. We've spent decades optimizing power delivery using those technologies. So today we are going to focus on controlled heating using both ERH and TCH. What you will not hear us discuss today is steam injection or steam enhanced extraction. Rarely will TRS recommend it. Its applicability, due to the uncertainty associated with pressurized fluid injection into the subsurface while heating, is just something that TRS does not recommend. So we are going to focus our efforts today, this conversation, on ERH and TCH, along with vapor recovery strategies to remove the steam and the soil vapor that's created while implementing a thermal strategy in a bedrock setting. So with that, I'm going to ask my first question. Susan, you spent a lot of time in consulting prior to joining TRS a few years ago. Why don't you open up this discussion by taking the time to walk through some challenges that came with your experience in Bedrock, whether that be delineation of the contamination or remediation. Why is Bedrock so complicated?
Thanks, Lauren. So for me, doing work in Bedrock is kind of like opening Pandora's box. We don't always know what we're going to find. It's daunting. It's hard to get to. It's expensive. There's a lot of challenges inherent with Bedrock investigation and remediation. A good case in point that I have from my consulting experience was in 2009. The state regulators required us to install 4 bedrock monitoring wells, kind of cardinal directions around the source area at the site, go down to the first water-bearing fracture, do some geophysics, install a monitoring well. So first phase of bedrock investigation. So the site is in the Appalachian Mountains, and there is a TCE contamination there from some former operations. Concentrations in the saprolite are up to 65,000 micrograms per liter, so indicative of potential DNAPL at the site. We installed 3 monitoring wells in Bedrock. We went to the first fracture, which was in 20 to 50 feet into the bedrock. Sampled those monitoring wells, non-detect. Pretty surprising, right? So then we go east of the site an area that was a little more challenging to get to with the drill rig. We set our casing at our PVC casing about 50 feet down, so tagged about 5 feet into rock, and then we started air rotary drilling. We got down to about 160 feet. So the hole was completely dry for 110 feet until we hit a water bearing fracture. The driller says, I think we're good. I think we got a fracture. So pull the tooling out. And, I said, where do you think water is going to be? And he looks down in the hole and you could see water. It looked like it was about 20 feet down. But literally, as we kind of looked up at each other and looked back down, water starts coming out of the casing. So we realize we have a flowing artesian well. We do go ahead and we're going crazy, getting drums, trying to plug the well, but we were able to do geophysics. We set a well. Turns out the well had about 20 feet of hydraulic head on it and was free flowing at about 5 gallons a minute. Beautiful mountain water. We thought this will be great. Well, it turns out it had 32,000 micrograms per liter of TCE. So we found the contamination. 110 feet into rock, next to the site. So it just kind of highlights the idea that before as you start a bedrock investigation, you don't know where it's gonna be. There are some general rules, but in general, you can also kind of toss out some of those rules. So there's many challenges to not only find the groundwater and find where the contamination is, but then how do we remove the contamination? Advective technologies like injection of chemicals, whether ISCO or bioremediation, are inherently challenging. I mean, how are you going to get into all the fractures where the contamination is? And then there's the idea here, as you've shown, of matrix diffusion. Over time, the contamination that's in those fractures is going to diffuse into the matrix. So, a lot of these remediation technologies, rely on contact between the chemical or the reagent with the actual contamination. And there's really no way to get into the matrix or the primary porosity of the bedrock with those technologies. So with bedrock, we've got the primary porosity, which is the bulk matrix of the rock, and then we've got the secondary porosity, which is the actual fractures. Well, the wonderful thing about thermal remediation is that we're heating the entire bulk of the rock. So the matrix of the rock and the fractures that are in that rock. Therefore, we're heating and volatilizing contamination in the matrix, which, as we know, over time, that matrix diffusion is a very big challenge, not only in overburden or not only in bedrock, but also in overburden where we have clayey zones. So, that the thermal remediation, heating the entire matrix up is a very big advantage to this technology.
Well, and that's Chris, you're Mr. Thermal Remediation, right? Your entire career essentially has been focused on thermal with, some time dedicated to vapor recovery, air, strategies in the subsurface. I guess let's talk about the physical removal of contaminants from rock and what technologies are available in that place in the industry. You've got excavation, not really very relevant. You've got vapor, multi-phase extraction, or thermal. So how impossible is it to use some of those strategies that I described?
Well, it's not impossible. It's funny. It's been great to prepare for this with Susan. But I think of NAPL removal from bedrock, fractured bedrock. These different strategies that we'll talk about some more. But it's refreshing to be reminded that the rest of the world doesn't know that this is achievable. That bedrock presents a big problem in the consulting world, a big barrier to it's a complex environment, as Susan just explained, to apply remedial solutions. And in my mind, we've been there, done that, and it's just tell me where we need to go, and we'll get there and get after it. Yeah. The strategies that we employ at TRS for remediation of these complex problems are the same we apply in the overburden, even when you have mixed geology, different sand lenses, different hydrogeology. Those can all be addressed through, of course, what's critical for us is a thorough conceptual model and understanding of the hydrogeology that's present in the contaminant profile. But we could definitely design a system that will affect and effectively treat and heat those different lithologic layers, and that includes fractured bedrock, solid bedrock, and the like. And as for the reasons Susan's pointed out, there are limitations in that porosity, and um, all rock is not created equal. Depending on um, the overall bulk resistance or the resistivity of that rock. If it's below about 500 ohm meters, we might lean towards ERH, and we might go to TCH above that threshold. But we've had success at some projects with high resistance, but with the secondary porosity being so high that we're able to successfully use ERH to treat that NAPL in those fractures. So, but I guess the point I was trying to get at is this, ERH, it doesn't need to contact the contamination. We can heat up the soil, generate that steam, heat up the bedrock, generate steam, and directly volatilize that contamination, and through fairly routine VR mechanisms, vapor recovery mechanisms, recover that contamination.
Yeah. I mean, and really these days we are looking at both technologies when we're evaluating a bedrock site, right? I mean, gone are the days where we're only looking at ERH. That certainly used to be a part of our history, just focused on ERH. But these days we're really, generating conceptual designs for both of those technologies that you describe when we're looking at a site for the first time, trying to figure out, well, which one is going to come in at a lower price point, right?
Yeah,
Um,
that's if at the end of the day, we wanted to provide a solution that's most cost effective for our clients for the problem that they have. And yeah, thank goodness we've when our learning curve has been slight, and I feel like our competency is um, well, we're ahead of pace, and we're very confident in that application of the TCH. In the last 5 years, we're up to 10 to 12, 15 projects with TCH, and have our little niche dialed in. So yeah, it's just trying to figure out what the circumstances are. That conceptual site model is key, but once we get that, we can further validate that conceptual approach through some testing if need be of that bedrock to further build confidence in the strategy. But yeah, at the end of the day, it's just having the right tools in the toolbox to solve the problems as they're presented.
yeah, yeah. So I mean, that brings me to Susan. Chris was just talking about the strategy. How do we end up putting these systems in place? I mean, Bedrock presents, a whole set of drilling challenges, right? It's not just as easy as spinning augers in the Vado zone anymore, or in the overburden, but how are we installing these systems in rock? It's all about that heating of the structure and the heat and the spacing between them. Care to comment on those techniques?
So typically we're using sonic for some of the softer rock, the sedimentary type rocks. We can use air rotary as well. Sonic, everybody does like to look at the soil core or the rock core that comes out, and that does give you some benefit of being able to see the actual rock matrix, to see where there's fractures. So there's some benefit to that. Air rotary or air hammer drilling is much faster to get to the target depth typically, and typically is going to target harder rocks. So some of the more metamorphic type of rock. Mud rotary might be another option for some formations. It's not something that I don't know that we have done it yet, but it's certainly it's a bedrock drilling technique as well.
Yeah, yeah. There's depth limitations, right? Or maybe not. How deep, would you want to go with some of these strategies that you just laid out?
So I think the only limitation would be, with the drilling technique. I mean, the thermal we can treat as deep as we can go. We've treated to depths greater than 100 feet in bedrock. But generally speaking, conceptually, most of the mass in contamination in bedrock is in that weathered overburden and into the upper portion of the bedrock. The fracture spacing typically decreases with depth, so that means there's going to be less contamination with depth. So, typically I think our clients are focused more on the upper portion of the bedrock where most of that contamination is, trying to target the highest zone of contamination in bedrock.
Yeah, yeah. So speaking of that zone of contamination, typically, the highly fractured, shallow bedrock zone, let's spend a minute there, Chris, because I know you and I have spent a lot of time together at some site working in that zone and trying to custom design power delivery systems in the field at that interface. What is happening at that, overburden rock interface? Can we go into maybe a little bit more detail about how we might customize that interface and customize power delivery deeper in the more competent rock versus overburden? And it looks like we've got a question coming in from Dave Shea as well, who really wants to understand how we judge the performance of those systems across that overburden to bedrock interface too. So we'll get into that as well.
Yeah, in terms of strategy, a lot of our work, about 10% of our sites, where well maybe it's 15%. We've done 23 so far, but a lot of times, especially the project you're referring to, is in a karst system with this highly variable uh, interface depth, and that presents challenges in itself. You've get DNAPL that's pooled in that near that interface and in that weathered zone, and maybe even a couple of those fractures on top. So, and again, this strategy is developed in conjunction with the consultant that's done the investigation. But at this one site, we decided to have the driller reach the interface of the bedrock and then then take that hole another 8 to 10 feet below that interface to make sure that we were through the weathered bedrock zone and through these first round of highly dense fractures to make sure that we were able to heat below where the gross contamination was, where the NAPL was in that weathered zone. Um, and and you might ask, the drillers we had sonic drillers drilling in real time. We had 2 rigs at this one site, this very large site in Alabama. And we had a whole construction team set up on the side. So as soon as the driller was able to report that bedrock interface depth, we knew that we had another 8 feet to go. We'd report that to the electrode constructors, and we'd be able to customize this secondary element that was focused, that was designed solely to be able to heat that bedrock portion of the site. We had a separate element that would apply energy to the overburden, which would typically be at a different voltage. But we were able to customize in real time with this highly variable bedrock overburden interface. And that's what's shown here in this map that we put together after the fact. It was kind of neat, just representative of a karstic interface, just highly variable, lots of hills, lots of valleys, lots of peaks. And it's really difficult to, it would be impossible. I guess ultimately what I'm trying to say is to flip it around. A lot of times we've got an overburden site, they give us a box. So, well, you need to treat 10,000 square feet down to 20 feet below grade. It's a nice clean box. Have at it. We can easily design a system. But here, we've got an incredibly complex system that we're able to customize real time to make sure that we targeted that area that contained the NAPL.
Yeah, so, with regards to just making sure we get to Dave's question, with regards to monitoring the performance of a system like this, I would want to point out, Chris, and please, fill in, but hopefully folks can see my mouse. There's a variety of temperature monitoring locations. There's these tiny little green triangles that are scattered throughout this entire treatment volume. They are located in the very middle of a triangle of heating infrastructure. So technically at the coolest point. And, we are monitoring throughout the entire depth interval, the treatment. At this particular site, I believe we use, Chris, was it every 5 feet or 3 feet? Usually our sites are between 3 and 5 foot intervals, but there's temperature monitoring that occurs throughout the entire treatment depth that ensures we are heating up the bulk matrix, not just the fractured zone.
Thanks for the reminder. Temperature monitoring is a key parameter for to ensure that any system, whether it's ISTR in the overburden or overburden Bedrock or just Bedrock, but we've got to be able to have the ability to apply the energy, but make sure the energy is having a real and measurable effect, and that temperature monitoring is key. And as Lauren mentioned, it's typically done in the middle of that triad of electrodes or heaters, where it's going to be the most difficult to heat. But that is a key metric in any ISTR process.
Yeah, just a quick follow-up question about, the need for groundwater extraction. I know the site we were just looking at, I happen to know that groundwater was flowing very slowly through that treatment volume, but some sites we do see groundwater flowing through, especially that weathered zone, right? Would you comment on groundwater extraction strategies we've utilized at sites like that where we need to slow down groundwater flow?
Yeah, it's again, we're reliant on the data that's provided about in the study that's been done on a site, but with that proper information, we've employed upgrading to pumping to help control groundwater movement through a zone, especially whether bedrock or overburden or sand seam, whatever the case may be that's creating this concern. It's advantageous for ISTR to control that groundwater flow to minimize heat losses. Energy is an expensive component uh, of the whole process, and if we can manage that effectively with upgrading pumping, we will. But it's a very it's just another tool in the toolbox to help solve that problem and help make sure we're providing the most efficient design for our clients.
Yeah, but what about, staying on the extraction topic, can you talk about some of the vapor recovery designs we've utilized? What's
Yeah.
important, in that treatment volume?
Extremely. Yeah. It's it's got to be customized. I keep on going back to, each site's different. Each site requires its own strategy because, as Susan pointed out earlier, these systems can be complex depending out, for doing a full bedrock treatment will require one strategy. If we're just dipping our toes into the upper couple feet of bedrock, that'll require a different strategy. Depending on groundwater flow, will require some thought. But the first strategy typically is what we'd call our baseline vapor recovery, which is venting in the vadose zone, and that's all driven by a negative pressure gradient that forms as we heat. We've got the steam that's being extracted through this highly permeable column that's occurring every 12 to 18 feet across this entire site, and proven a way to have effective capture. Depending on the complexity of the site, we might extend that screen to make sure we're intersecting different intervals of concern, increase the depth of the screen. In some instances, we can do multi-phase extraction in situ. Again, it depends on that's least desirable because that ends up in more energy removal through groundwater extraction. So it's a tool in a toolbox, but it requires more energy. So therefore, it's least desirable. But it's definitely a strategy we can and have implemented. And then, Susan, maybe you talk about some of the unique things that was done at your site in Scotland, where they took a very conservative approach in extraction and monitoring.
Yeah, for the Hamilton project, which is located in Scotland, we used multi-phase extraction. It was the multi-phase extraction wells and infrastructure were installed before we drilled the electrodes. Actually, there was a lot of concern about mobilizing contamination during drilling of all of these electrodes. Yeah, so this is a map of that site, and you see all the blue dots are surrounding the treatment area as well as inside the treatment area. And those were brought online before we started drilling the electrodes because they wanted to have capture of any contamination before it might migrate off-site. This was a highly fractured sandstone aquifer. There were nearby receptors. There was a creek where the groundwater was discharging to that was, up there where Lauren's mouse is. There were also to the bottom of the page, those were residences. So there was concern for if contamination migrated in that direction, would it become a vapor intrusion problem for those residences? So it was a very conservative approach. We did end up, as Chris was mentioning, you are during operations, where we want to extract the steam, but we don't want to extract groundwater and everything all at once so that we're having to apply more energy. So it was a stepwise approach. We began as we began heating and extracting steam, we began turning off some of the multi-phase extraction wells because each of those electrodes themselves had a vapor recovery point. So it wasn't necessary to continue operating all of the multi-phase extraction wells during operation.
Yeah. Mike Aberton has a question in the Q&A right now about the design and the optimization of these systems. So hopefully that answered the question, Mike, there for you. But it's certainly an iterative process. It definitely was on this site in Scotland, right, Susan? It was a constant optimization and adjustments being made in the field.
Definitely.
Yeah. Perhaps you continue and just talk through some of the results that were achieved.
So this site, like I said, there were a lot of concerns about receptors. There were high concentrations of TCE here. They were indicative of NAPL or DNAPL. There was a highly fractured sandstone that was overlying a mudstone. The mudstone had much less fracturing, so the most of the contamination was up in that sandstone. We installed electrodes to, I believe, about 43 feet, 12 meters. I have to reverse
Quickly do that math.
So we treated to 43 feet. I think there are 46 or so electrodes here. We had all the multi-phase extraction infrastructure. We had a lot of temperature monitoring, both inside the treatment area and outside the treatment area to make sure we weren't, for lack of a better word, pushing contamination out. And what we found was that, no, we did not increase the temperatures outside the treatment volume, which was great news. So overall, we ended up, concentrations, like I said, at this site were over 200 milligrams per liter. So pretty darn contaminated. The goal was to get to less than 5 milligrams per liter. And in most cases, we got to less than 1 milligram per liter. So a very, very successful project. I included this graph here to the right just to depict kind of what happens during thermal remediation, specifically this sandstone remediation. First the concentrations in this well were around 40 milligrams per liter, but as we start heating and as we begin desorbing the mass out of the matrix, it becomes dissolved into the groundwater. Therefore, we see this peak of contamination in groundwater, which then goes away over time. So it can be alarming to see that, but that's exactly what's happening. Is it's dissolved either if it were from soil or from bedrock, it's desorbing from the actual particles or the matrix and then dissolving in groundwater, which then becomes which then is steamed and the contamination is removed. So
I think it's probably worth pointing out that this data point right here is relatively high, right? But 5 months later, so after the thermal remedy has been deemed successful, that data right here, I'm trying to use my mouse, where is it? That data point right here is ultimately, Susan, what you and your team used to then shut off the system.
Yep, that's correct.
5 months duration right here.
Mm-hmm.
And maybe if you have I know we have a temperature plot we might show, but just to show how that matches up with there was a great explanation, Susan, about that dissolution of, or yeah, the contaminant going into solution that caused that spike. But that was about week 6. And you can see just as we're getting to this curve, maybe this is a different site in Pennsylvania, but maybe that's around the 70, 80 degrees C mark as we're starting to directly volatilize that any NAPL that's present, stuff is going into solution. And then a couple weeks later, we're up at boiling, and that the boiling curve shifts because again, all these RTDs or temperature monitoring points are located in the hardest to heat areas, but there's boiling that's occurring close to these electrodes. But this represents the worst case. But that sort of matches up exactly with what Susan was showing on her other site. That we've got things starting to happen around 70, 80 degrees C, maybe 6 to 8 weeks into project operations. And by the time we get to 8 to 10 weeks in operations, we're generating steam full bore, and that mass recoveries and removals occurring full bore.
Yeah, yeah. Thank you for making that point. Chris, I know that we have a ton of stories about our thermal sites, but also are developing a lot of stories about our bedrock sites. Would you comment on, how many bedrock remediations we've done and give the audience an idea of where in the subsurface we focus these efforts, deeper, shallower in the fractures, etc.
Well, sure. Yeah, thanks for sharing this slide. I talked briefly about this one strategy that we employed in Alabama, but this at TRS, we're proud to report that we're just above 200 sites completed in our nearly 25-year history. Just fantastic to be along for this ride. But we've developed these strategies based on our clients' needs over time. But so we've completed remediation now successfully in 23 sites out of those 200. So yeah, maybe 12% of our work is done in Bedrock. But of those 23, about half of them we're targeting this overburden Bedrock interface plus some depth, 4 feet, 8 feet, and typically that's applicable in a NAPL highly weathered zone and in a karst environment that's highly variable. Like, well, we just can't give you a bottom. So we do this customization in the field. It allows us to be extremely flexible with this extremely complex working environment, like
Yeah.
custom real-time fabrication.
Yeah, thanks, Chris. I've got a follow-up question from Fred Sims. Hi, Fred. You don't know this yet, but maybe the idea of this webinar came from a conversation you and I had somewhat recently, but nonetheless, so Fred asks about guarantees and, are we willing to guarantee some of these strategies in specific concentrations in bedrock settings? Fred's comment is specific to groundwater guarantees, MCLs specifically. But if you could take a step back maybe and just talk through our experience with guarantees and how we have done some groundwater MCL guarantees in the past. Yeah, I'll turn it to you, Chris. And Susan, I know you live this too on your end as project manager, so perhaps you chime in as well.
Uh, yeah, guarantees are something we've done and will entertain. I think we have the experience to support, guarantees. The way we consider a guarantee because there's risk and unknowns in any subsurface environment. But we at the same time do have 200 sites of experience meeting goals. Um, there's a balance. And so we have a standard fixed price, which is sort of an energy target where we, based on all this experience, where we think we're going to get to achieve that goal, we can come in with a more cost competitive price at that with that strategy, and that employs a little bit of risk sharing where we can provide value. But if need be to get to an MCL in a guarantee, that is something we can definitely entertain at a slightly higher price, depending on those risk variables, how well the subsurface is defined, how well the contamination profile is defined, and the like. But that is definitely something we've done, and definitely something we can entertain.
Yeah, Fred, hopefully that answered your question. We've got a number of different questions that we might take the time to ask. Before I dive into the audience questions, Susan, Chris, any other particular site stories you want to tell this audience as I get ready to more thoroughly go through the audience questions that are coming in?
We talk about our southeastern Pennsylvania site that was our first full bedrock treatment that was sandstone with coal seams,
Yeah.
um, 20 feet of overburden and 90 feet of rock. Um, and it was actually a six element electrode, highly complex. Yeah, and we might do that a little bit differently these days. Maybe go with three to reduce the complexity, but we wanted to make sure we were able to attack this complex heating media as effectively as possible. So the whole idea behind a separate element is that gives us the ability to operate each element at a different voltage. And one of the keys, this is ERH, electrical resistance heatings, and one of the keys for that functionality is just to have that voltage match the impedance of the soil. So, in theory, the impedance of clay would be very low, sand might be a little bit higher, and bedrock even higher. And so we have these uh, highly, very complex power control units that control the voltage we apply to each element. And again, to bring it full circle, the points of these six element electrodes would be to apply a different voltage to each element to effectively match that impedance of the soil that we're seeing. In hindsight, we could have gone a little simpler, maybe go with three, but that was the intent.
This is that small little treatment area, right, Chris?
Right behind a factory there there was an active plant, and some backdoor dumping that occurred, or maybe it was a tank, I forget exactly, but it was part of their plant operations, and we were able to get in there and get that site heated and up to temperature. I think that last plot showed that we might have been at temperature in 2 months, and we're able to achieve our goals by 90 days. So it was just site heated up very well, very effectively, and met our goals rapidly.
Yeah. And nowadays for especially with, deep applications, we're actually submitting proposals right now where we are recommending thermal conduction heating as well. We are finding we're resistivity, electrical resistivity may not be available for the rock. So that presents some uncertainty when it comes to electrical resistance heating. So, TCH is certainly very well suited to meet goals, and it's a technology that TRS is comfortable with, and have submitted, several proposals recently where we are recommending just that strategy.
Exactly.
Yeah. So I am just going to share my screen again, and then we can go into the more formal Q&A, not just my ad lib trying to ask some of the questions that folks were asking along the way. So Ross submitted a question about the contaminants that we go after. So I think we've spent a little bit of time talking about VOCs, but we haven't mentioned other contaminants. So could we comment a bit more about I don't know, maybe PFAS projects? His question is specific to perchlorate. So yeah. What kind of
Well,
PFAS work are we doing these days?
well, we do have, and we'll have. I wasn't prepared to talk about this, but we did. Perchlorate was a co-contaminant in Alabama, and I could have sworn that uh, there was sensitivity to it. Yeah, so I apologize for not having a complete answer. We can certainly get back to you, but I did think we they have performance metrics that we could report on in a positive fashion. But that's my recollection. I remember that there was concern from the base ahead of time and no concern after our treatment. But I hadn't prepared to address that question, so we can definitely get back on that. But in terms of PFAS, yeah, it's we're using TCH, thermal conduction heating, to heat up soil in situ and ex situ extremely effectively. The in situ project, we learned that we needed to get above 400 degrees Celsius to reach non-detect levels. Um, and we have an ex situ soil pile where, we got the average soil temperature to 625 degrees Celsius. So it just, overperformed there for good reason, and that's being sampled. When it comes to bedrock systems and PFAS concerns, again, temperature is the key. So then we're to a TCH range, as you may or may not know. ERH is really limited to the boiling point of water at depth, but it's still going to be far short of the temperatures we need for effective PFAS remediation in bedrock. But at the end of the day, if the conditions are right, um, TCH would be a very effective mechanism for moving PFAS in 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 bedrock or weathered bedrock or overburden, as the case may present.
Yeah. So Susan, there's a question about the funding for these projects. I am curious, your project workload, are the majority of them government funded? Does TRS Group help support Fortune 500 companies with their thermal remediation strategies? Could you comment on where a lot of the funding comes from for our projects?
I would say both. A lot of private funding for various projects. It's all driven, especially for private firms um, or companies. It's a lot of it's driven by the risk. Is there an immediate risk to a receptor, or do we want to get this project or to get this property redeveloped? So private companies have various different reasons for wanting to do thermal remediation. A lot of the government funding is either based on, yes, risk. Is there a risk to an aquifer? Obviously we've had the infrastructure funding a couple of years ago. We do have quite a few projects that are being funded by that bill. And those projects are selected based on, on risk as well. The projects that I've done, there are risks to drinking water supplies. And so EPA has elected to use thermal to remediate the source areas that are, above or adjacent to drinking water supplies. So yeah, I would say both. It really does vary.
Yeah. And a follow-up question is just simply how much does a strategy like the ones we've discussed today cost? So Chris, you want to take that one, maybe per cubic yard?
Well, I was gonna flip it back to you. I guess I have an idea. There's definitely a range, and it always depends on how clean is clean. The gentleman asked about MCLs. Now that's gonna up the price because it's gonna extend out the amount of energy we need to add to boil out that very small amount of mass until we're done. If it's just an apple removal, that's going to be on one end of the scale. Even when it's in bedrock. But so if my take would be for a range would be 125 bucks a yard to 450 bucks a yard, depending on a wide variety of factors. So Lauren, hopefully that fits in with what you might expect.
I think that was a great non-answer.
That's
No, I love
easy.
it.
If
Yeah.
it's harder, it'll be more expensive.
Dave Cacciatore, he has a question about evaluating different technologies, especially when it comes to bedrock treatment. So, is there a particular parameter, conceptual site model parameter that you're looking at? Do you care to comment on what matters most?
I guess it depends on the extent. Sorry, Susan, I'll give my take on it, but I'm thinking about northern Alabama. If the karst, if the bedrock is understood, and there's relatively good understanding of the contaminant profile in that bedrock, if it's weathered, um, and there's a concern about groundwater, all signs point to ERH. If there's relatively little presence of water and the rock is more competent, at that point, I think we definitely lean towards TCH. But so understanding the groundwater situation, hydraulic conductivity, and if you're leaning towards a full bedrock formation, then at that point it might be nice to have some bedrock samples to test the resistivity to confirm that TCH might be the best. But
Yeah.
that good conceptual site model and a full understanding of the hydrogeology is really key to help try and determine which would be the best technology.
Groundwater flowing through the treatment volume is a really important data point too when it comes to removing the heat that we're putting into the subsurface, right? So we are very sensitive to that groundwater flowing across the treatment volume. So that's going to be an important criteria. ERH, can deliver power if it works in the rock. ERH can deliver power at a higher rate, so it can overcome more groundwater flow, whereas TCH is a lot more sensitive to it. That's another data point. Sometimes our clients have a preference too, quite frankly. So we'll, follow their lead. If they really like one technology over the other, we can certainly work with them on that
Yeah,
front as
yeah.
well. Yeah.
Yeah, we can certainly bid to spec, design to spec, and then provide recommendations along the way based on and data. Yeah, but yeah, that groundwater flow, groundwater movement, and the nature of the rock and the extent of rock would be the two key parameters, I would think.
So you brought up Northern Alabama. Jeff had a question earlier that we didn't even get to, but he brings up land subsidence and those issues when working in a karst environment. Could you, could either of you comment on how those are addressed during the installation of a thermal system or the operation of a thermal system?
I can, yeah, Susan, feel free to interject. In our experience, we know that does occur naturally. In
Yeah.
our experience, especially in Northern Alabama, I know they were concerned about voids. Um, I don't know, Lauren, we must have drilled 500 points, you
Yeah.
know, in that area, and maybe we had one or two electrodes sink a foot or two that
Yep.
we're able to modify and correct in the field. So in terms of installation issues, we had extremely minimal, 0.05% of concern, and they were, took us now to correct. Post remediation, I've heard no reports of changes in that geology that would have resulted in subsidence. I think one of our clients would have brought that to our attention rapidly if there was some sort of post-treatment effect. So,
And we've done monitoring of buildings. We've obviously treated underneath buildings, and many clients have a concern about the structural integrity of the building. We can use various devices, crack monitors, or so on to see if there's been any subsidence or damage to the building. And I think in our experience, we really haven't seen anything. So we understand the concern, but it really is minimal to no issue there, really.
And to put a finer point on it, ERH, less of a concern, TCH, depending on the temperatures you want to get to. We've already talked about PFAS. We're treating PFAS under a building and getting to these high temperatures. That's definitely something we're going to pay attention to. That would definitely have an impact. But with ERH and the temperatures we're talking about, we're only moving a percentage of the soil moisture. So the the overburden characteristics don't change dramatically from a load standpoint.
Yeah. So I know we have several questions that we have not yet answered, but I do want to be sensitive to everyone's time. We did go over by about 5 minutes, so we'll include here shortly, but I do want to stress the fact that as a follow-up, we will provide this webinar as a video for everyone who attended and for those who registered but were unable to make it today. We will also follow up to everyone in attendance with written responses to all of the questions received. So I apologize. We have run out of time and aren't able to get to all the questions, but I do appreciate all the engagement today from the audience. That engagement is truly what keeps us continuing to produce these webinars for everyone. So thank you for your time today. Look forward to another webinar announcement coming this fall from TRS and the Bringing the Heat team. All right, take care, everyone. Thank you,
Yep.
Susan. Thank you, Chris.
Thanks, Lauren. Thanks for being here.
Okay.